Now that we know about the existence of the dual and the primal, let's talk a little bit more about the relationship between the primal and the dual. The reason for this is because this is required to develop the network simplex algorithm, which we'll talk about tomorrow. And also we will be referring to it when we speak about the integer programming solutions the day after next. So we're talking about the relationships between the primal and dual models. I'm using interchangeably primal and dual problems or models, and I will be assume the primal is maximizing and dual is minimizing. That's arbitrary. Okay. Now at optimality, we've observed these things, that the primal objective value, which was 11.5, is always going to be equal to the dual objective value. So this is not just for this example, this is true in general. When we solve the dual and we observe the dual solution, we notice that the dual solution was equal to the primal shadow prices. That was the 0.5. And similarly, the primal solution is equal to the dual shadow prices. That was the 2.5 and 4.5. That is at optimality. What is also true, we didn't observe this, but sorry, is that if the primal has no feasible solution, and the way you detect that is in the two-phase method. After phase one, you still have artificial variables in the basis, has no feasible solution, then the dual is unbounded. So if it solves, then they both have the same objective. But if it doesn't solve, then the dual can also not solve. And so, but it doesn't solve for a different reason. And the same thing is true the other way around. I shouldn't put equal, I should put that implies, and that is implied. If the dual has no feasible solution, as you might guess, the primal is unbounded. So that's at optimality. That's the first part of the relationship.